Hello everyone! In this video we will continue to examine topic 5.2, the heating effect of electric currents, resistance and resistivity. In the last video we introduced this concept of resistivity as a way of sort of tying resistance to the actual material. Remember that resistance is defined as the ratio between the potential difference in the current, but empirically, as a matter of sort of experimental results, it is connected to all kinds of straightforward properties of the material. So for a single material with resistivity rho, length L, and cross-sectional area A, the resistance of that material is equal to rho times L over A. Now, it's important to distinguish between resistivity and resistance, and unfortunately they do sound sort of very, very similar. But recall the difference that we introduced in topic 3 between extensive and intensive properties. Recall that an extensive property is a property that sort of depends on amount, okay? It's the property of a particular object. An intensive property is a property that is independent of amount. So, resistivity is a lot like density. It's a property of the material itself, not an actual object. Whereas resistance can change if you literally change the object that you're holding, rather than just the material. Some example resistivities are given here. They cross an absolutely enormous range. And you can see that there is a huge difference between the resistivity of pure water, for example, and the resistivity of copper. Unsurprisingly, copper has a very, very, very low resistivity because there's a lot of free charges to carry charge through it. Notice that metals change their resistivity, and tungsten can change its resistivity when the temperature changes, and it does so pretty dramatically. So as the temperature increases, tungsten is a typical metal, which means that its resistivity also increases, and this is about a factor of 10 between tungsten at 20 degrees Celsius and tungsten at 1500 degrees Celsius, and that's a pretty big deal. That is a significant difference in resistance, even though both of those numbers seem very small for a given material. It's literally 10 times as resistive at higher temperatures. Just for a brief explanation of this, this is due to the fact that at higher temperatures, electrons and other charge movers are moving around much faster, and they sort of get in the way a little bit. So if you imagine sort of people in a room sort of milling about and you're trying to get from point A to point B, if the people in the room are standing very still, right, if they're standing still basically, it's very easy to get from point A to point B. If they're running around all over the place, even if it's just the same number of people, so they have a lot of kinetic energy, it's harder to get from point A to point B. And that's exactly what's going on here with the resistivity. So I'd recommend taking a look at these two examples and making sure you're comfortable with applying these formula. It's also important sort of to take a look at this equation, R equals rho L over A, and make sure we understand sort of the fundamental reason why each of these things are true. Okay? They seem reasonable, they're totally reasonable from a qualitative sense, but we can actually do better than that. We have equations that sort of can show why this is true. So consider, for example, length, right? If the resistance is defined to be the potential difference divided by the current, and the potential difference is defined to be the work per unit charge, recall that the work in question is the work done by the electric force. And so it's the electric force times the length per unit charge. And so what that means is that for a given current, all right, assuming you want to keep the current the same, then the resistance R is proportional to delta V, and that delta V is proportional to Fe, so the electric force, dot L times the length divided by the charge. And so assuming the general electric force being applied to those charges is the same and the charge itself is constant, that suggests that the resistance itself will be proportional to the length of the resistor. All right? So that's sort of why R is proportional to L here. Notice all those assumptions we had to make. It's important to recognize that this equation is really applicable to a single piece of material made of the same material with a very clearly identifiable length and cross-sectional area. So if it's a sort of chunky piece of metal and mixed things, for example, if it's a phone, it has a resistance. You know, you can put it in a circuit and figure out what the resistance is, but you wouldn't be able to calculate it using this formula. And so every time we said you need to assume such and so is the same with the current, the electric force, and the charge, those assumptions all go into this. All right, cross-sectional area. So same kind of idea. We're going to unpack this formula a little bit. So we say that R is defined to be delta V over I, but we have another formula for the electric current as it relates to the drift velocity. And the current is equal to the number of charge carriers times the area of the current carrying element times the drift velocity of the charges times Q. So for constant delta V, you can see that the resistance is proportional to 1 over the cross-sectional area, because that I formula gets plugged in to the denominator in the definition of the resistance. Finally, you can sort of simply consider the material. So why does the material affect the resistance? Well, different materials have different numbers of free charges, conductivity, and most do vibrate more as temperature increases, increasing the resistivity and the resistance, which we just talked about.